Learning, and we're in Chapter 6, and we're just starting the applied questions, so question 8. So this has several parts, so you can read this if you want, but we will just kind of push through and look at each question in its own turn. Okay, so first we'll tackle parts A and B, and all we're doing here is we're just generating some data. Okay, so I'm going to use 100 observations and 10 predictors, right? Because why 10 predictors? Because later in this set of questions, we will be selecting models in which we have up to 10 predictor variables. Okay, and each of those predictor variables is going to be a polynomial of x, right? So it's going to be x to the first power, second power, third power, as well as an intercept. Okay, so we've generated our data for x, and that's what we're supposed to do for part A. And then in part B, we're going to create another variable called y that follows this expression right here. Okay, and we're going to have y equals an intercept plus beta 1 x1, beta 2 x squared, beta 3 x cubed. Okay, and we're going to set the values for beta 0, 1, 2, and 3. All right. So the way that I'm doing that is I'm just assigning a value to beta naught. Okay, I'm just giving it a random value here. Okay, from a normal distribution, and then I have the rest of the betas. I'm calling it B, and I'm just generating 10 random values from a normal distribution. Each of those comes with a mean of 0 and standard deviation 10, right? So this is just to give us some values for the betas. And then I have an epsilon term here. Again, just a normal random variable with mean 0. I put standard deviation 2. That's just arbitrary. And now I'm generating y according to that equation. So I grab beta naught, and then beta 1 times x, beta 2 times x squared, beta 3 times x cubed, plus the epsilon term. Okay, so that's part A and B. All right. So now in part C, okay, so in part C, let me run that. Part C, we're going to use the regsubsets function that's discussed in the book, and then perform best subset selection. And to determine the best model, we're going to use three different metrics. Okay, so CP, I think that's AIC, then BIC, and R squared. All right. So let's do that. So for that, you will need to install the Leaps package. I've already installed it, so I'm just commenting it out for now. And load the Leaps package. I've ran this once, but now I have different data loaded. I've generated some different random data. So we're going to use regsubsets, and I have my equation here, y being regressed on x, and so when I put poly x10, that gives me x1, x2, x3, or x1, x squared, x cubed, and so on, all the way up to x to the 10th, using my data frame. Okay. And then I'll get a summary output of it. And I want to show which of the models is best. So I need to minimize CP or minimize BIC or maximize the adjusted R squared. Okay. So I'm going to do all that and then plot the results here. Okay. So when we look at this, so let's look at the matrix first. Okay. So this is telling me the best models. So this matrix here is coming from this. Okay. And it says which terms are part of the best model according to the three different metrics, right? The top one is CP, second one is BIC, then adjusted R squared. And so we see that for CP and BIC, the best model is what is in fact the true model here, which is the third degree polynomial, right? So we have true intercept, or the intercept is included, the first degree x, second degree x, third degree x, and then every other term is not included. Adjusted R squared wants to throw in, oh, actually adjusted R squared gives us the same result. Sometimes it's just a little bit different. No, it actually is different. Because if I come over here, we see that adjusted R squared for just sampling bias also wants us to have the 8th degree polynomial there, right? So anyway, so here I'm plotting the AIC and BIC and adjusted R squared, and then singling out the best model according to each of these here. Okay, so that's fine. So now again, let me clear that because we have different data loaded now. So now we're supposed to do the same thing, but now use forward selection. So doing the same thing, but with forward selection. And so that's what I'm doing in this first code block, as well as backwards stepwise selection, which I'm doing in the second block here. So let's just run both of these. Okay. And so for the forward selection, you can compare the results here to what we got above, but they're identical. So the same models are selected. And then for backward selection, again, we pick out the same models, okay, as we did for forward selection and for best subset selection. I don't know that this problem will always work out that way, but every time that I've ran through this, it does. I don't know why it should always do that, but it should do that most of the time, I would guess. So, okay. So now for part E, again, clearing out my output. So we're going to do something similar, but now we're going to use lasso and use a cross-validation method in order to select the best model, right? So just a quick kind of overview of what's happening here. So we're going to run a lasso model on a training set of data, and then from that training set of data, we'll have our model. And then we will use cross-validation on a testing set of data in which we're trying to pick out the optimal value of lambda, which again is this modulator in the lasso that is telling you how heavily to penalize your function to arrive at an optimal fit. Okay, so you'll need to install and then load the glmnet package, and I've already installed it, so I'm commenting it out. And so first we need to generate some, we need to break our data down into training set and testing set. And so I am going to train on 75% of the data. You can modulate that. Okay? And so that will come, and so how many observations is 75%? Well, it's this expression right here. And so now I'm going to pick this many samples from my data. So I'm just going to randomly sample across my data set with this sample function. Okay, so I'm sampling. So I'm going to generate, train in random numbers. Okay, that will serve as an index, and every observation in my data frame that is of the row that is included in training index will be included in xtrain, and if it's not included, it will be an xtest. Okay, and then I'm doing the same thing for ytrain and ytest. Okay, so I have my training data ytrain or xtrain ytrain, and then my testing data xtrain or xtest ytest. Okay, and so now I run my lasso, and so this is so first we need to set up different values of lambda, and so we're just calling this grid by the naming conventions in the book. Okay. And then I use my my glmnet function, setting alpha equal to 1, and that gives you the L1 norm, that gives you the lasso. If we put that to 2, we would instead have ridge regression. Okay, and we're testing every value within grid here, so we have a bunch of values for grid. Okay, for lambda. Okay, and now I am going to use cross validation. Okay, so now I'm testing that model against the training data. Okay, and this is giving me the error from each lambda value, and then I select as my best lambda the lambda that produces the minimum error. Okay. And now I make new predictions from this model using the best lambda and using now my test data. Okay. And yeah, so let's run that. Okay, and so in the end, what we get is well, we get a couple things. So first, we get our plot here, which is the estimates of mean squared error against all of these different values of lambda. I guess it's actually log lambda here, in which the minimum lambda is picked out, or the best lambda is picked out. Okay, and then we also get our which terms are included in the model. Okay, and so we see that this gives us up to the third degree polynomial, which is the correct model. Now, in the past, when I've ran this, let's just see what happens here again. Right, so in the past, when I've ran this, there is apparently some stochasticity built into these algorithms here, because it will give me different, never mind. Well, it will give me different values based on what is being partitioned into the training set and the testing set. Okay. So, so in this case, it did not give us the correct model, right? It wants to omit the second degree polynomial here. But anyway, so now here for part F, we're going to do the same thing, but now, well, what are we going to do? We're going to generate a new y variable that looks just like this, so it just has the seventh term of x. Okay. And we're going to perform best subset selection as well as lasso, and then just compare the results. So, let's do that here. So here I have, I've generated my new data. So y2 is just this now to correspond to this. Okay. I'm just creating a new data frame. That's data frame 2, where I've replaced the y variable with y2. Okay, with this guy here. And then I'm just copying and pasting the code, but making sure that I'm using y2 as my new variable here. Again, we have a different model. So we'll run this one, which is the best subset selection, and then we will also do the lasso down here. Okay, so so for best subset selection, depending on which method we're using to define the best model, we get the 7th degree polynomial for CP as well as for BIC, and then the adjusted R squared wants to give us the up to the 8th degree polynomial being the best model here. Okay, well, let's compare this then with what happens with the lasso. So here we have the results of the lasso. Okay, and this one also wants to give us up to the 7th degree polynomial. Okay, so in this case, the two methods agree, and what is kind of interesting about these two models is that even though we know that our model is X7, the best subset selection wants to give us these 6 additional terms here, which is just kind of an outcome of using polynomial of a single variable, right? So all the variables are related in a very particular way. But anyway, we will call that good.